Welcome to this brief screencast on our third abstract data type, the queue. So what are queues? They're a model of waiting in lines, or also in certain places they're called queues. In the United States we call them lines, but in other countries they're called queues, so you join the line or you join the queue. It supports fair processing in the sense that the person at the front of the line or the queue gets served before the last person. So it has some principal characteristics. Queues are first in, first out. So when you join, if you're the first one to arrive, you're the first one to get out of the queue. They have a size. We know how big they are. We can say how many items are in the queue. But unlike lists, we can't actually get at the things in the middle of a queue. You can only get at things at the front of the queue. You enter at the rear and you leave from the front. So you can only access things at the front of a queue, whereas things are added to the queue at the end or at the rear. So we're going to talk about let's talk about the interface first. The public interface queue, we have two methods for adding things to the rear of the queue, two methods for seeing what's at the front of the queue, similar to like a stack. You have the peek method, so you can see what's at the front without affecting it. And we have two methods for removing something from the queue. The reason we have these two methods is that one of the methods throws an exception if there's a problem. The other one returns a special value. So we'll talk about add. We add to the rear of the queue, but if the queue is full and cannot be expanded, it will throw an illegal state exception. The offer method will not throw the exception, but will return false if you cannot add E to the end of the queue. The element looks at the retrieves, but does not remove the head of the queue. If the queue is empty, it throws a no such element exception. The peek method does the same thing, but does not throw the exception. It will return null if the queue is empty. The remove method will retrieve and remove the head of the queue or the front of the queue. If the queue is empty, again, it throws a no such element exception. The poll method does the same thing, but if the queue is empty, it will return null instead of throwing the exception. And lastly, size returns the size of the queue. The size method is from the collections method, so if you look in the Java docs, it doesn't list size as one of the methods on the queue, but I'm listing it in mine because you can ask the size of a queue. So here's the 7 methods for a queue and interface for the queue. And so we're going to talk about an implementation of the queue with using a link structure. Next screencast we'll use an array. So we'd have the two different implementations of queues, one using link structure and an array. Today we're just going to talk about the linked one. So we use nodes just like we did in our linked list. It has no wasted space because we only have nodes for the items in the queue, whereas in the array we have extra space. Excuse me. There's no copying of elements. We don't have to shift things around in the queue. We have a front and a rear. The problem is it's a slightly complicated implementation because we need the inner class. We got to keep track of the front and the rear. We got to keep track of size. It's not overly complicated. It's less complicated than the list because we don't have to access things in the middle. We just need to keep track of the front and the rear and the size. So just like we did for the list, front you could think of as the head and rear as the tail. The Java doc for queues talks about removing from the head. We're actually removing from the front. So you can use the variables are the same. The names just give it a little clarity. We move from the front, add to the rear. So we also need our inner class node. And since we have a one-way thing where we add at one end and we pull from the other, we don't need a doubly linked node. We can have a singly linked node, so we just need the singly linked node. For the constructor, we need to initialize all our member variables, so we need to initialize the front, initialize the rear, initialize size. When we create an empty queue, the front is null, the rear is null, and the size is 0. So we can detect whether it's empty by just seeing whether front or rear is null, but also more easily check for size equals 0. So let's talk about the add and offer, how to put things into the queue. So we're going to add the entry to the end of the queue, the rear of the queue. We have the entry. So what do? We add to the end of the queue. We increment the size because we keep track of the size, and then we return true. If we had a fixed size queue, we would throw an exception. But since we're using a linked structure, we don't need to have that. We can always add to a linked structure. If you want to implement a linked queue with a fixed size, you would have to keep track of its capacity somewhere. And then if size equals capacity, you would throw your exception. So there are two cases here with a add. If size is 0, that means we've got to update front because there's nothing there, so we have to update. We add the entry to the rear, we point front to the entry, we increment its size, and then we can return true. So we create a new node to hold the thing. Its next pointer is null, and we point rear to it. We then point front to it, and this is a special case because front's got to be the point to the front of the queue. And if the size is 0, front didn't point to anything. We increment the size to 1. We could have done size plus plus if we wanted to. And then we return true. And we've done that. So now let's look at this other case. So if size is not 0, we say rear.next equals new node. And again, we set its next pointer to null. We put the value in there. We update rear to point to the new end of the queue. So rear equals rear.next. And then we increment the size plus plus, and then we return true. And the big O of the add method is big O of 1 because we're just adding something to the rear and updating some pointers. There's no looping, there's no traversal. It's very simple. We didn't have to start at front and go all the way to rear because we keep track of both of them, so big O of 1. The offer method is similar to add, but instead it does not throw an exception, it returns false. So a simple way to do this is you try to add, and if it throws the exception, you return false. So we can try to return the add. If that succeeds, we returned true, and the entry is in the rear of the thing. If the queue had a fixed size, or for whatever reason we throw the illegal state exception, we return false, and that indicates that we failed to add offer failed to add the thing to the end of the queue. And again, since add is big O of 1, there's no looping. The big O of the offer is 1. And I like this of using the code. Instead of duplicating the code here, I like using the try catch. It just makes my code more compact. Element and peak, again, that's element is the one that throws the exception. If it's empty, if it's empty, throw the exception, else return the head of the queue. So if it's empty, size is 0, we throw a new exception, else we return the head of the queue, which would be front.data, and since we're not updating it, we just return the data, and we're done. Again, big O of 1 operation. Peak, again, instead of throwing the exception, it will return no, so we can try calling element. If there's an exception, we return null, so we return element, which would return the front of the queue. Else, if we catch the exception, then we return null. Again, element's a big O of 1 operation. We have no looping, so this is a big O of 1 operation. And again, I like the try catch because it's simpler. I could have copied the element code in here and said if it was empty, return null instead of the throwing the exception, but I like this method a little bit better. Remove and poll, this is how we actually remove something from the queue. So we retrieve and remove the head of the queue. It returns the head, the thing that was at the beginning, or it throws an exception if it's empty. Again, remove is the one that throws the exception, so if empty, we throw our exception. We remember the data at front, because once we update front, we've lost a handle on that node. We then update front to point to front.next. We decrement the size, and then we return the value that we remembered, and we are done. So the big O of 1 for this operation. Again, it throws the exception if empty. The poll method doesn't throw the exception, it returns null. So we try to remove. If there's an exception, we return null. So we try to return the remove, we catch the exception, and return null. Again, big old fun operation. And then lastly, size, we return size. Very simple. We implemented our own queue, and it's fairly simple, although we do have to keep track of front and rear. We have to understand about the inner node class. Not that complicated, nice, but there's a simpler solution to implementing your own code. We just use the Java linked list class. The Java linked list class implements the queue interface. So we just create a variable type queue, .q in this instance, and we assign it a new linked list instance. And now, because the type of the queue is the interface, we can only call the queue interface methods. So we can only we can't do the get and set methods or add in the middle that the linked list supports, because the interface restricts us to just the queue interface. And that's a much simpler solution. If you want a queue, I would use this way versus implementing your own. You might as well use what Java provides. Thank you very much for your attention.